Good afternoon. We start the third session. This is a double session. First, Patrick Cheridito from Polytechnic de Zurich will present the talk of efficient regression, Jaguar-Stein, Byzantines, and normalizing flows. Patrick is a professor of mathematics in Polytechnic of Zurich. He's the director of the RiskLab and FinsureTech Hub, and he's also member of the AI Centers and head the data science group of the Swiss Association of Actuaries. His interests are in stochastic modeling, mathematical finance, quantitative risks, and insurance mathematics and machine learning. We have a double presentation in this session. Patrick will we use the half of the session approximately, was the idea, feel you free. And the second part will be the third part of my presentation that yesterday, remember, I say that today I finish my presentation. We will have the coffee break, and after the coffee break, we have a session with Juan Luz and Nuria that they provide you any explanation, any question about the team groups, the project student, and then we will distribute the 8 teams in the different places of the building for to start to work at 6:30 approximately. Then you can start the things and to start to discuss and to discuss and to think about the project that you have together. And as you can check in the program, we have different in the afternoon. Usually we have different slots for working together in order to discuss and continue the collaboration. Well, Patrick, please. Thank you very much.
Well, thanks so much for having me here. So this is on efficient fair regression, and interestingly, it's connected to Wasserstein-Boris Center. So I will use elementary mathematics. So please ask if you have questions. Who knows the Wasserstein distance? And who knows what a Barry Center is? Most of you, I guess. So, okay, I try to explain these concepts and how it's related to fair regression. So this froze right now.
Unplug. Yeah, normally it works for me. I mean, there should be a computer scientist somewhere in the room.
Yeah, I'm not. So. Okay. Perfect. So this is about the insurers. So they use an increasing amount of data to price insurance policies. So somehow they become like the big tech companies who collect more and more data. So this leads to more precise estimates of individual risks. So as more data they have about you, the more precise their estimates are what kind of risk you pose to them. Okay. On the other hand, this goes against the idea of solidarity in insurance. So some countries have prohibited use of certain characteristics. So for example, in the EU, it's prohibited for insurance companies to use the fact whether you're a man or a woman. Okay, so they have to treat you equally. Some countries prohibit the use of age, ethnicity, religion, whether you're married or not, credit score, zip code, so this is where you live. employment status, education level, and insurance pricing. Okay. On the other hand, machine learning models are trained to minimize prediction errors. And if you do that, you can implicitly encode and amplify existing biases with respect to sensitive attributes as gender, ethnicity, and religion. Okay. So, for example, in insurance pricing, the risk prediction might be correlated with some predicted protected characteristics. In credit scoring, predicted default probabilities might systematically differ across demographic groups. In hiring, the predicted performance scores could exhibit discriminatory effects. So the goal of this talk is to formalize demographic parity, which is one concept of fairness in regression. There are others, but demographic parity is one of those that is widely used in a regression setting. Okay, and so we want to show that the optimal fair predictor is characterized via optimal transport theory. Okay, so there is an interesting connection between a fair regression and what is called optimal transport theory, which has been widely studied recently in different areas of mathematics and also in machine learning. So the key mathematical concept here is the concept of a Wasserstein barycenter. Okay, so a Wasserstein is a distance between probability distribution, and the barycenter is the weighted mean between different distributions. Okay, and then if I have time in the end, I will also say a few words about the efficient numerical methods for computing Wasserstein barycenters. So in the first part, I tried to explain the concept, and then in the second part, I also tried to say a few words how it can be computed efficiently. Okay, so let's say we have a data generating model, and so here I have a random vector x, s, y on some underlying probability space omega, and x is features d, okay, and so these are non-sensitive, these are open, so you're free to use them. Okay, so this could be age in car insurance, or the type of your car, or your driving experience, these kind of, so these are open, right? And then I have sensitive features. Okay, so this could be gender, ethnicity, or religion. And I'm kind of not allowed to use those to discriminate against you. Okay, and then I have a target variable that I try to predict. Okay, so this could be the costs if you bought an insurance policy from me. So that would be the costs that you're going to cause in a year, for example, because you have a car insurance, or it could be a credit risk or something like this. Good. It could also be multidimensional. So, for example, in insurance, one often tries to predict frequency of events and the average cost of an event. Okay, and those two could also be correlated. Okay, but for the moment, we're thinking of the target variable y just as one-dimensional, say a cost that you're going to cause if I'm selling you an insurance company. Okay. Then what is standard regression? So standard regression just seeks a predictor, which is a function, which depends on all these variables, the open ones and the protected ones, which minimizes the mean squared error. Okay, so this is the expected squared difference from my prediction from the actual target. Okay, so I guess you have seen this before. So this is standard regression. So the best unconstrained predictor here would be F pure, okay? And we know if we try to minimize the mean squared error, the best predictor is the conditional expectation, okay, of my target variable, given the open variables and the protected variables. Okay, so for everybody is familiar with the concept, I guess, right? Very good. So another question for us is, how do we constrain F, this predictor, so that it does not discriminate protected groups? Okay. But I still want to stay as close to the best prediction, F pure, as possible. Okay? And so here we're going to use this concept of demographic parity. Demographic parity means the following. So I have a predictor F that is using both variables, the open ones and the protected ones. Okay? But what I want is that the conditional distribution of my predictor, so that would be the left side here, given that the protected variable is in one state, for example, given that you're male, should be the same as the conditional distribution of my predictor, given that you're female. Okay, and this should hold if I have several categories of protected variables. It should hold like the distribution of your predictor should be the same, conditioned on all possible values that the protected variable takes. Okay, is this concept clear? Yes. Very good. So the distribution of the prediction has to be independent of the sensitive feature. So the interpretation is for each group S, we denote the conditional distribution by mu S. Okay, this is the conditional distribution of the predictor given that I'm in a particular group, say male or female. Okay, and then I require that all these conditional distributions are equal. Okay, and so this is not an easy constraint. Okay, you're trying to solve an optimization problem now, a best prediction problem, but under this constraint. And that's not an easy constraint. It's a distributional constraint and is much richer than saying the conditional expectation is the same, for example. So this is also a concept. It's called mean parity. Okay, so what's our problem now? So the fair regression problem now is I still try to minimize the mean squared error. So I try to find a predictor that is as close to the target as possible in this mean squared sense. But F has to be fair. Okay, so F has to satisfy this constraint here. Good. So this concept of demographic parity is also known as statistical parity or group fairness, and there is literature about this. Okay, so the concept is clear. Yeah. Very good. So, but now you might ask you, okay, why don't I just solve this regression problem by ignoring the protected variable? Why wouldn't you do that?
There might be correlated.
Exactly. Exactly. So one naive idea would be, okay, I'm not allowed to use the protected variable, whether you're male or female, for example, or what your ethnicity is or where you live, right? I just use the other variables for regression. So I calculate this, the g of x is just conditional expectation regressed on the allowed or the open variables x. Okay, problem is this does not guarantee demographic parity in general. Why? Because X is typically correlated with the protected features, okay? And so if you do that, then this regression will not satisfy the demographic parity principle. So the conditional distributions will not be the same because X typically correlates with S. Okay, even though you didn't specifically use the protected variable S. This is called proxy discrimination. Okay, so as a consequence, if you want to achieve this concept of demographic parity, you have to actively modify the prediction distribution, not just dropping S from your prediction. Okay? So the key insight here is if we denote these conditional distributions by mu s, the problem reduces to finding a common target distribution that I call nu here. And for each group S, a map, TS, that pushes the conditional distribution that I get from my pure regression problem to this fair distribution nu at some minimal cost. And so this is exactly an optimal transport problem, okay? What's optimal transport? So this was introduced by Gaspard Monge a long time ago, and Gaspard Monge was an interesting character. He was a minister during the French Revolution, a mathematician, and he was also a co-founder of the École Polytechnique in Paris. Okay, and his wife, his wife's family owned mines. Okay, so maybe this was one motivation why he started thinking about this problem here. So on the left side here you have different mines. Okay, and then on the right problem you have factories where people build something with the ore from the mines. And then the problem is how you're going to transport what you're mining here on the left side to the different factories. Okay, then in a mathematical formulation, Morse problem is this thing here. You have X, which is one location over here. And then you transport it with some map T, okay, over here, okay? And then you integrate this whole thing over the original distribution mu dx, okay? And you want to do it in such a way that you transport the distribution mu to your target distribution nu. Okay, so in a picture it looks like this, okay? So you have some initial distribution over here. Think of it as a pile of sand, for example. And now you want to move every grain of sand over here. So every grain of sand x here is transported to T of x. Okay. In general, there is different ways of doing this. Okay. So you could move like the leftmost grain here to the rightmost part over here, or you could move the leftmost grain over here to the left part here. Okay. But typically what you're doing is you're introducing a cost function c, which depends on x and T of x. And you want to minimize the average cost, okay? So you calculate the cost and then you average over the initial distribution. And that's Morse transport problem. Okay, then what's the Wasserstein distance? Say for the cost, you just take Euclidean distance. It's like how far Tx is from x. You square this. You integrate with respect to the initial distribution. You take the square root. And you call this W2 between mu and nu. Okay, so now the nice thing is, turns out this is a distance or even a metric between probability measures. Okay. So it's like a Euclidean metric between points in space. This is a metric between different probability distributions. And this has given rise to a lot of nice mathematics, especially in recent years. Okay, so in analysis, in economics, but recently also in machine learning. Okay, now what can we do if we have a metric? We can calculate barycenters. Okay, say I have different distributions, pi 1 to pi k, and then I can define the pi-weighted 2 Wasserstein barycenter as the distribution that minimizes this sum here. Okay, so in a sense it's the distribution nu that sits in the middle of all these distributions, pi 1, pi 2, pi k. So in particular, if you say all these initial measures are point measures on points x1 to xk for some points in Rn, then this notion of Wasserstein barycenter just becomes the usual barycenter, which is just a weighted average of these points in Rn. Okay? Once you have this notion, you can also calculate averages of distributions like this here. So here I have 4 extreme distributions on the corners here. I can calculate different averages of these distributions in the Wasserstein sense. Okay? So you've also seen these pictures where one phase morphs into another phase. And so this is done with these Wasserstein averages. Okay? So here I can compute averages between those, between those, between those. And I can also compute Wasserstein averages between all 4. Good. So how is it connected now? So going back to our fair regression problem, by Pythagoras, I can decompose the mean squared error from my target variable to my best fair prediction into an irreducible error, which is the distance from the target to the pure prediction, plus the distance from the pure to the fair prediction. Okay? So if I want to calculate or use a fair prediction, I'm losing accuracy. Okay? And what I'm losing here is this excess risk due to fairness. Okay, so I'm losing a bit of prediction power. But on the other hand, I'm fair. Okay, so this is because the pure regression is just the L2 projection on all measurable functions that depend on X and S. Okay, now I want to reformulate my problem. So I can write the fair predictor as an L2 minimizing function. Okay. From F pure. So instead of approximating the target variable Y, I'm now approximating the pure prediction. Okay. So now you ask, oh, why is this a complicated problem? I can just like calculate another projection or something, but you cannot, because the set of fair predictors is not convex. Okay, so you cannot compute this as a projection or like a typical projection problem. So a standard Hilbert projection theory does not apply here. Okay, but what I can do is I can decompose this mean squared error over the protected groups. So I can write this mean squared error as a sum over all protected groups. I write the probability that I'm in protected group S here. I sum this over all protected groups. Okay. And then what I see is I'm searching for like a probability distribution that is minimizing this sum, where mu s are just the conditional distributions of my pure regression. And so what we're looking for is the pi-weighted 2-Wasserstein barycenter of the conditional distributions of my pure predictor. Okay, so that's the relation between fair regression and this concept of Wasserstein barycenters. It's clear to everybody? Or? Yeah?
Is that expression like a...
So now I didn't hear you.
Is that expression a proper square root? Do you have any guarantee of finding that new?
Yeah, okay. So that's a good question. I mean, I'm making here implicitly a couple of assumptions that everything is nice and then this thing exists and is unique. Okay, but there is also boundary cases where that's not the case. If you have like discrete distributions and they're not so nice, but I don't want to go there, right? Okay, but in our setting, so this problem has a unique solution. Okay, and what I should have said, we're not only looking for the barycenter of these distributions, but once we have the barycenter, which is the fair distribution, we also need transport maps that transport from mu s to the fair distribution for every s. Okay. So now let's see how we can calculate this. Okay, and first I do a 1D target space. So for example, you only try to predict the cost. So Y is one-dimensional. Your feature space might be high-dimensional, but your target is just one-dimensional. Okay, and so here I'm writing, so let's assume mu and nu here are atomless probability measures, so they have no point masses, so they're like nicely, continuously distributed. Then the optimal transport map from mu to nu is this thing here, okay? So, and this is kind of, I mean, you can prove this, but this is kind of obvious. So you take the cumulative distribution function of your two one-dimensional distributions, f mu and f nu, okay? Then you invert the first one, and you apply it to your first distribution, okay? What happens? You get the uniform distribution, okay? Then once you have this uniform, you apply the cumulative distribution function of your first distribution to the first distribution, gives you a uniform. Then you apply the inverse of the second cumulative distribution function, and this transforms into the second distribution. Okay? And this transformation is also monotone because both these transformations are monotone. And if you have not seen this before, it looks maybe strange to you, but this is intuitive because what it means is if you transport one-dimensional distribution to another one, you move the most left point from the first distribution to the most left point of the second distribution, and so on. You don't mix, right? Good. What you can also show is this expression for the square of the two Wasserstein distribution. It's just the integral over the two quantile functions of the two distributions. The inverses of the cumulative distribution functions are the so-called quantile functions. So what you do is you write these two quantile functions, you integrate from 0 to 1, and that's an explicit expression for your two Wasserstein distance between the two distributions. Okay? So once you're there, what you can also show, and that's not too hard, is the barycenter distribution is given by its quantile function. And what you do is you use all the quantile functions of your marginal distributions, and you take a weighted average of those. Okay, gives you another quantile distribution, and that's the quantile distribution of your barycenter distribution. Okay, again, if that's new to you, looks maybe a bit weird, but it's natural to believe, at least, that this is true. Okay? So the Wasserstein-Barycenter averages quantile functions, not densities. So say your marginal distributions have densities, don't average the densities. Also, don't average the cumulative distribution functions. What you have to do is you have to compute the quantile functions. You have to average those. Okay? So then, what's the fair predictor if you have a one-dimensional target function? And that's going back to this paper here. It's you use your pure predictor. That's the best possible predictor. Okay. And then you check what value your protected variable takes. And then you transport from there using the transport function that transports the S marginal distribution into the fair distribution. Okay? So what you have to do is you don't ignore the protected features. Okay, you have to use them. And then you compute the best predictor, okay, which uses the open variables and the protected variables. Okay. Then you compute the conditional distributions of your best predictor given S is equal to all the little s, like given that you're male or given that you're female, for example. Then you compute the quantile function of your barycenter distribution, and you use it to define this transport map that transport mu s to nu. Okay? So each group's predictions are optimally transported to a common target distribution, the barycenter, which is the fairest compromise among all distributions. Okay? So again, if you want to go through this process of fair regression, don't ignore the protected variable, compute the best prediction, and then transform it using these transport maps here. Okay, it's clear, or do you have questions?
For me, what's not clear is that not. Well, I will wait. What's not clear is when to apply this tool, because not always the data is unfair. And how do you distinguish when we have unfair data and we need to apply this fair regression method with all the disadvantages or disadvantage possibilities that it could have?
Yeah, it's basically given to you maybe by your own policy or by regulation. So again, in the EU, for example, if you work in an insurance company, you have to do this. You're not allowed to discriminate between men and women, for example. So if you're just going to use all your data and you run the the best regression, typically you will discriminate between men and women, for example. Your prediction conditioned on being a man or conditioned being a woman, for example, will be different. And so implicitly, you will treat these two differently.
So the suggestion is in edge cases is when policies tell you to do it, you will use it and that's it, even in edge cases. Okay, thank you.
Great. Any more questions? Okay, so this was basically the concept and how you can compute this if your target variable is one-dimensional. And the last part is how you can compute this if your target variable is multidimensional. Okay, so now I say my target variable is in Rn and n is 2 or higher. Okay, so how can I compute this fair regression problem here? And so what turns out that you have a nice formula here. So let's say you have a probability distribution pi over the protected groups, okay, that you're not allowed to discriminate against. And let's say you have probability distributions mu1 to mu k, which now are distributions on mu n. Okay, let's assume you have some, in the background, you have like an n-dimensional random vector with an easy distribution. Typically, that's an n-dimensional normal distribution that you're going to use. Okay, then what you can show is you can write the minimization problem, which is a bit complicated. But the important thing is you can write this as a minimization problem. Okay, so in the end, you can use some kind of a machine learning model, say a neural network or something, to try to approximately solve this minimization problem. Okay, and also the pi-weighted 2 Wasserstein barycenter will be given by the distribution of H, okay, where H is a weighted sum of these G functions that solve this minimization problem. So this is a generalization of the concept that I've shown you in 1 dimensions, where the barycenter was given by the quantile function, which was a weighted mean of the quantile functions of the marginal distribution. So here what I have to do, I have to solve this minimization problem. It will give me a function g which depends on x and s, and then I have to take a weighted average over the protected groups of this function g, and this will describe my barycenter. Yes?
After the optimization process, do you ensure that what you obtain is symmetric or not really?
Well, theoretically, this has to be a metric, but now I'm not interested in the metric anymore. So now I'm interested in this function h, okay? And I will also be interested in this function g, which will give me the transport maps that I'm going to show you in a second. But this is a computationally hard problem. I mean, especially if y is high dimensional, and especially if I have many groups here. So if k is large. So this is computationally hard now. Okay, and then okay, what I will need is these transport maps here, which now are given to me by g and h, these two functions that I characterize here. I mean, this is a theoretical characterization. Now I'm asking myself, how can I compute these things? Yeah?
I have a small question. I guess in the decision problem, are we averaging over the dimensions by indexing over n? Or
No.
why we are like summing up to?
No. So n is the dimension of the target space, right? So say I have a 2-dimensional target variable now, right? So what I have to do is I have to average over the categories that I have, how many different protected subgroups I have. So there I do the averaging.
In the decision problem, like above in the part in item A, there is the summation, and also there is a subindex I over the G.
Yeah. Here?
Yeah.
Yeah.
Yeah. So we
okay, so here you have to compute this sum and you have to try to minimize this. Okay, so you minimize these over all possible functions g, and I didn't explain this very carefully. So there are some constraints to the function g which you're optimizing over.
Okay.
But in the end, I mean, let me just try to continue here because I want to talk about one more thing. But in the end, this is a complicated minimization problem. The good thing is, and it has constraints, okay? The good thing is I can write this as a minimization problem, so I can just use a machine learning tool in a sense, right? So I parameterize all of this with a neural network and I do gradient descent on this, and this works pretty well. Okay, once I have approximate solutions of G, I define H, and then theoretically I solved my fair regression problem in high dimension. Okay, so now I don't know how much, should I take another 5 minutes or so?
Yes.
Because I wanted to introduce another thing. So first I have a little illustration here. So first you do the unfair prediction, which is the best prediction, okay? So you don't care, you're unfair, okay? Then you calculate the conditional distributions of your predictor over group 1, 2, down to k. And then you calculate your barycenter, and then you have to transport all your marginal distribution to the barycenter. Okay? Then you also have this thing here, the price of fairness, okay? This is how much accuracy you lose by being fair compared to using the best predictor. Okay? I mean, if your best predictor already is close to fair, then it's not a big problem, right? But if your best predictor is very unfair, so it treats different protected groups very differently, then you have to correct the loss. You have to correct the distributions, and you also pay a higher price of fairness. Okay, and that's just this expression here. Okay, and so now maybe in the last 5 minutes I wanted to talk about normalizing flows. Okay, what are normalizing flows? Anybody?
They are invertible transformation of a distribution function.
Very good. So it's a generative AI model, okay? So there is different generative AI models, simpler ones, more complicated ones. Maybe the most popular at the moment are the transformers because they're used in the LLMs. But normalizing flows also have some good properties, and we're using them here. And so in the last 5 minutes, I'm just trying to explain how we use normalizing flows to solve this problem numerically. Okay, so that's a deep generative modeling via invertible maps. Okay, so the goal is to model some distribution on Rn so that it fits a given data set. Say you have like data points in Rn, okay, and now you want to construct a distribution that fits these data points. Okay, and so one way of doing is you start with like an easy distribution. So most cases you start with an n-dimensional standard normal distribution that I'm denoting by p set here. And then you transform it. And the idea of normalizing flows is you use a sequence of rather simple transformations. Okay, so this will help you also to invert these. But you use a lot of them to have expressive power. Okay? And the idea is to start with a simple standard distribution, apply a sequence of transformations, such that your final distribution here is the distribution that fits your data. Okay? And you want to do this with invertible maps, because you need to go forward and you will also need to go backwards. Okay, and so from analysis 1, you know that the one-step density transformations, if you do transformations like this, is given by the determinant of your Jacobian. Okay, so this is just how, if you transform, you have to adjust your measure because you're going to extend space or you're going to squeeze the space. Okay. So this differential here is the Jacobian matrix of your transformation. And then also, don't look at this too carefully, but you have an expression for the likelihood. Okay? And so what you're doing is you're training these transformations here, up here, so that you're going to maximize the likelihood of your data. Okay. How do you model these one-step transformations? With affine coupling layers. So the idea is you split your input data into two parts, A and B. Then you pass one part, you just pass it through. Okay? And the other part, you transform with an affine transformation that depends on the first part. Okay? Why is this clever? Because the inverse transformation of this is as simple as the forward transformation. You just have to subtract and then multiply with exponential of minus this thing here. The Jacobians become lower triangular, so the determinant will just be the product of the diagonal, which is written here. Okay. And the functions S and T that you're using here can now be arbitrary neural networks. Okay, so these can be very complicated, but the structure of the transformation is still simple. Okay, and so now what we do is we use these normalizing flows to solve the problem that I wrote before. And just to wrap up, there's a small numerical result here. So this is a communities and crime data set. That's a US data set on where there is a lot of data. There is like 127 features. And then there is how many crimes happened in a neighborhood and how many police officers worked in this neighborhood. Okay? And that's an open data set that is usually used in connection with these fair regression problems. So the target variables are percentage of officers assigned to drug units and total number of violent crimes per 100,000 people. The non-sensitive features are 127 socioeconomic characteristics. And as a sensitive feature, we take here the percentage of the population that is African American, which is between 0 and 1, but we discretize this into steps 0, 0.01, 0.02. So these are 100 different protected subgroups I have here. Okay, so computationally, this is a pretty hard problem. And so what I'm showing here is what happens if I run a standard regression. Okay, how is the outcome correlated to my protected variable? And so I'm calculating 3 different correlation coefficients. Pearson is like the standard correlation. Then is Bierman and Kendall. These are 2 different measures of correlation. And what I see here, if I run a standard regression, I have high correlation between my predictor and the protected variable. Okay? And then if I run my method here, I get these correlations here, which are almost 0. Okay? So this computation works. This is some of the references that I used, and if there are more questions, you can ask now, or you can also ask me later.
Is this compatible? Because as you mentioned, it's very computational. It needs a lot of power about computation. Yeah. So is it compatible to reduce the space into a latent space, change with the flow, the fairness, and then regenerate the data again, so it's easier to compute?
It's a good question, but I don't know.
Okay.
Yes?
I was having a question, but I think you already answered it. It was, what do you do when you have a continuous variable in the subset of S? So you have to discretize it, right? Or could you make a convolution instead, or?
We're working on this right now with a PhD student. Mm-hmm. Okay, because like the traditional fairness literature is typically is like you have finitely many categories, like men or women or different religions or different ethnicities. But we're working with a PhD student on this question, so we try to extend some of the formulas we have here. I think you just write an integral over instead of a sum. But then everything else we're working out right now. And then how you compute it, I don't know, whether you discretize. I mean, you can always discretize, right? Or you use some other method, I don't know yet.
Okay, thank you.
Sure, yeah.
Following this discretization problem, will this framework also work if we are working in discrete settings and, for example, using total variation distance instead of Wasserstein?
I guess you could use total variation distance. You just lose the connection to the fair regression definition that I use here.
Okay.
I mean, the question is what happens with this whole framework if you use a different notion of fairness. As I said in the beginning, what I'm using here is demographic parity, which is one concept of fairness, but it's not the only concept of fairness.
Okay.
So what and on the other hand, I have a Wasserstein barycenter here, so I'm using the Wasserstein distance. So these two relate to each other. So now you can change your concept of fairness over here. You can use your distance between probability measures over here, but then you don't have the same complete story that I have. You have to check how it connects, right?
Okay. I was curious about the generative model you mentioned. It seemed similar to diffusion models. I don't know if it's similar or I just...
Well, in a way it's similar, except diffusion models are continuous time, you then discretize it, but this is discrete from the beginning. And there is no diffusion, so it's just a sequence of deterministic transformations.
Okay. And also, I was curious if you have like more than one protected variable, how should you assess or implement this?
Well, this fits directly, right? Because say you have two, but both those are
you can combine
discrete.
them.
Then like 2 and 2, I have 4. So this.
Okay. Okay. Thanks.
We start the secret match.
Thanks.